Welcome to iTTV for Form 5 Physics. The title of this lesson, the ripple tank. In this lesson, we want to have a look at the phenomenon known as reflection of waves. And in order to study the reflection of waves in the laboratory, we use the ripple tank. The ripple tank is an instrument that basically allows us to make waves in a laboratory and to be able to observe these waves. We'll have a look at the ripple tank in a moment. Let's begin the lesson. Sea waves. Strong waves move towards the beach. When sea waves move towards the beach, the waves are reflected back to the sea. We can view the waves like that using a ripple tank in the physics laboratory. The diagram you see in the slide is a diagram of a ripple tank and the waves produced by a ripple tank. So that is what a ripple tank is. And this over here is the ripple tank. The main parts of a ripple tank are obviously the tray in which we put the water. Over here we have a motor that will vibrate either a source that will produce circular waves, or on the opposite side a source that will produce straight plane waves for us. Above the tray is a light. As the light is shone through the waves, underneath here on a piece of paper it will produce a pattern of the waves. The pattern will consist of bright lines and dark lines that will represent the crests and the troughs. As you see the ripple tank in action here, as the vibrating source touches the water, waves are being produced. As we said earlier, we can produce either plane waves, which are straight waves, or we can produce circular waves. The images of the waves can then be projected onto a screen as we show you now. The wavelength and also any changes to the waves can be easily observed using a ripple tank. Waves, a ripple tank. Straight waves or circular waves can be produced in a ripple tank. These waves have alternating crests and troughs. Crests are like a convex lens. They focus the light to a point. This will create bright lines. Troughs are like a concave lens. The light diverges as it passes through a trough area. This will produce a dark line. So in a ripple tank, what we get are consecutive dark lines or bright lines. The distance from a bright line to the next bright line will represent the wavelength. Or conversely, the distance from a dark line to the next dark line will also represent a wavelength. Reflection of water waves. Reflection of water waves using a ripple tank. As you can see in the diagram, parallel wave fronts are reflected back. We can see waves reflected in such a way that the angle at which they approach the barrier equals the angle at which they reflect off the barrier. This phenomenon is called the reflection of waves. The incoming waves are called incident waves, and those bounced off are called reflected waves. The normal is an imaginary line perpendicular to the reflecting surface. The angle I is called the angle of incidence, and the angle R is called the angle of reflection. So these are the key things on reflection. A wave that is coming in will be reflected off a surface and will bounce away. The wave coming in will produce an angle that we call the incident angle, and the reflected wave will have a similar angle that we call the reflected angle. According to the law of reflection, the angle of incidence is equal to the angle of reflection. I is equal to R. And as we said, the normal is a line that is drawn perpendicular to the reflecting surface. Let's go up to the board and have a look at how water waves reflect off a surface, and let's put the surface at a few different positions so that we can work out this reflection phenomenon. So let's say that we have a surface that is plane, like so. So let's say that we have a wave that is incoming. Let's say we have plane waves. So we have a plane wave coming in, like so. So the wave is moving in, and here is your reflected surface. Now, when you're drawing these reflections, always remember any wave that comes in at 90 degrees to the surface will bounce back at the same angle because it is approaching at the same angle as the normal. So as this wave comes in this direction, as the wave strikes the barrier, it will bounce straight back. So our reflected wave, which I'll draw with a yellow dotted line, will go straight back like so. Now that is when the wave approaches at 90 degrees. But what happens if our surface is at a slight angle? So let's draw a surface that is slightly angled like so. Now, if my waves are approaching this, let's draw 3 wave fronts here. So we've got a wave approaching like so. The best thing to do in a circumstance like this is to just continue with the line of propagation and work out its angle of reflection. Treat the diagram as if it is just a light ray that is reflecting off a surface. So, what we are saying is extend this line until it strikes the boundary. Draw in your normal. Remember, your normal must be at 90 degrees to the surface. So this will be your normal. Now, your incident ray has to reflect, and remember the angle of incidence, which is this angle here, must be the same as your angle of reflection, which means this angle here must be the same. So, if I was to draw this angle in here, like so, this angle, R, should be the same as this angle. Although my diagram is not the greatest, you understand the idea. Once you've drawn your reflected propagation, then draw in the lines of your new wave front. Remember, you should always draw your wave front also at 90 degrees to the line of propagation. And that's how you'd complete a diagram that showed reflection of a wave. But what about other types of waves? What about a circular wave that hits a flat surface, or a curved wave that hits a curved surface? We have a variety. Now, in each case, the best thing to do is exactly what I suggested earlier, which is maintain a straight line using the line of propagation. Complete drawing the line just like you were doing with a light ray, and then fill in all the wave fronts. So let's go and do another one now with a circular wave hitting a straight plane surface. So let's say I have a straight plane surface like so, and from here, this point, I have a circular wave being produced. Now, like I said, what we do is we draw a line of propagation. In this case, the wave is coming out in this direction, and over here, it's coming out in this direction. Continue your line, draw your normal in, and then bounce your wave off. Same thing over here, continue your line, draw in your normal, and then bounce your wave off. Now you've got the 2 lines for your reflected wave. connect these together, and you get your reflected wave. So like I said, whenever dealing with reflection, continue with the line of propagation, reflect it back. Once you've got all your reflected lines, then fill in the wave fronts, and you should get an accurate reflected wavefront. Waves move in the same medium of equal depth, same wavelength, the incident wave and the reflected wave, same velocity, incident wave and the reflected wave. What we are saying here is, as long as your depth of water in the ripple tank doesn't change, the velocity and the wavelength will be unchanged as well. In fact, the only thing that's going to change is the direction of the wave. So velocity, wavelength, amplitude, frequency, all of these factors are unchanged. This is a common question in an examination. What changes during reflection? Remember, the only thing that changes is the direction of the wave. Discussion. Sound waves too are reflected the same way. So sound waves, also a wave, is also reflected. Sound waves tend to be reflected off hard, smooth surfaces. Once again, the law of reflection applies. The angle of incidence must be equal to the angle of reflection. Take a bell and a half-meter rule. Let the tube be placed at an angle to the laboratory tabletop, reflecting surface. Keep a soft board vertical to the tabletop. Ask a friend to ring the bell. Take another rule on the other side of the screen and keep it near your ear. Change the angle of the second tube with respect to the plate. At a particular angle, you will be able to hear the ringing of the bell very clearly. When you can hear the ringing of the bell very clearly, this means that the angle of incidence is equal to the angle of reflection, and you're getting good reflection of sound. Sound in the hall. Sound which has been reflected off the wall is called an echo. Like other waves, sound reflection best occurs from flat, hard surfaces. The natural echo of a room is called reverberation. Materials which are soft and uneven, like curtains, carpets, and cushions, absorb sound much more than they reflect it and decrease reverberation. Let's try an exercise. Complete the diagram above when parallel water waves are reflected by straight aluminium barrier. So here we are asking you to complete the diagram. What you have here is something very similar to the diagram we have here, where our plain water waves are hitting a surface at an angle. So remember what I said. So please do this now. Extend your line of propagation till it strikes the surface. Draw in your normal. Remember, your normal should be at 90 degrees to the surface. Then draw your reflected wave. Once you've done that, put in your wave fronts. Once again, remember, your wave fronts should be at 90 degrees to the line of propagation. Have you done that? Good. Let's try another question. The voltage supplied to the vibrating block is increased. Explain what will happen to the velocity of the water waves. So I'm basically increasing the voltage. So over here, our ripple tank, just imagine that I'm using an extra battery or increasing the power supply. So what happens to the velocity of the wave? Well, this is sort of a trick question. I said earlier that the things that affect the velocity and wavelength are the depth of the water. Now, I'm not changing the depth of the water. Now, if I don't change the depth of the water, what does this imply in terms of the velocity? Have you written down an answer? Let's have a look. Velocity remains the same because the speed of the waves depends on the depth of water. So basically our velocity is unchanged because the depth of water remains the same. Let's continue with the same question. The voltage supplied to the vibrating block is increased, but now what will happen to the frequency F of the incident waves? Once again, I'm changing the power supply, increasing its voltage. How will this affect the frequency? Have you written down your answer? Let's have a look. Answer. Frequency will be the same as the waves are from the same vibrator. As long as the vibrator, which is the instrument up here, is the same, I should get the same frequency. I'm not changing my source of vibration. So, frequency unchanged. Now let's try the third part. The voltage supply is once again, as we said, increased. So what will happen to the wavelength? Will the wavelength change too? Well, will the wavelength change? Have you written down an answer? Let's check. Answer. Wavelength will change according to the depth of water. Deeper water, the wavelength will be longer. So here, I'm not changing the depth, which means that the wavelength will be unchanged. Reflection of waves using a curve reflector. In this diagram, what you can see is we're using a concave reflector. The principal focus of the concave reflector is F. The reflected wave fronts are circular, converging towards and passing through the principal focus F. This can compare with a concave mirror converging parallel rays of light. So when I use a curved reflector, in this case a concave reflector, what occurs is very similar to when light strikes a concave mirror. The light is converged to the focal point and then travels on away. So what do you do when you have a diagram like this that you need to draw? Once again, do exactly the same thing as we said earlier. So let's sketch this diagram over here. Let's say that we have a curved surface like so, and I have a wave front coming in here. Now, remember what we said. You have a line of propagation here and a line of propagation here. Extend your line of propagation and complete the diagram. So, your line should continue on straight and then reflect back. Here, continue your line on straight and reflect back. The point where they converge, that will be your F. Once you've finished drawing the line of propagation and its reflected line, then fill in. So your wave becomes a circular wave that goes towards F and then extends out from F like so. So remember what I'm saying. Finish your line of propagation and treat it just as if it was a light ray. Once it's completed, then fill in all the other bits and pieces like the wave fronts. Curved reflected waves are produced in a ripple tank. Concave reflector show the waves are from the center of curvature in front of curved reflector. What about if we use a convex reflector? Here, it compares very similar to a convex mirror. Diverging parallel rays from a virtual focus at F, which is behind the reflector. So, if you have a convex surface, do exactly the same thing like we said. Complete your diagram and then finish drawing it in with all the wave fronts being put in. Once again, curved reflected waves are produced in a ripple tank. The convex reflector shows the waves diverged from the center of curvature at the virtual back of the reflector. So it came from the virtual F. Remember once again, Just the final key here, sorry to remind you about this all the time, but to complete your diagrams for reflection, complete or continue the line of propagation, reflect it, put in the normal, make sure I equals R, and after you've done that, draw in your wave fronts. Summary. Waves can be reflected by plane, concave or convex reflector. The velocity of waves depends on the depth of water in a ripple tank. Frequency of the incident and reflected waves are equal. The wavelength increases as the velocity increases. The wavelength and velocity are linked together. If your velocity changes, your wavelength will change. But remember, the only way to change these things, the velocity or the wavelength, is by changing the depth of water. So during reflection, velocity, wavelength, frequency, and the amplitude are unchanged. The only thing that changes is the direction of the wave. Remember, the key to reflection is the law of reflection, meaning that the angle of incidence is equal to the angle of reflection, and the angle of incidence, angle of reflection, and the normal are all in the same plane. That's all the time we have for this lesson. Thank you for watching ITTV.